Okay, so this is the classic Atwood machine. I guess Atwood came up with this magical pulley system. I don't know, but it's called the Atwood machine. Now, that's where you have two masses. Fortunately, they're different, or this would be a very boring problem. In the case of the system moving this way, M1 is clearly greater than M2. So probably the input values you were given were just that. Now, there's more information in this problem than you need. For one thing, this is an angular velocity, so that's pretty lame, because even though the wording of the problem wants you to find the rate at which the masses are moving after they've moved a certain distance vertically, and you're given that distance. The fact is they ask for the answer in meters per second squared. That, people, is an acceleration. So this, I must admit, this is a little bit confusing. Now, another little confusion is that this pulley does not rotate, so the radius of the pulley doesn't matter. So just, we've got a fixed pulley, we've got your classic physics string, no mass, no stretchy, no friction in the pulley, there's no motion of the pulley, we don't have to count for any energy loss due to the rotation of the pulley. We'll do that later this year. For now, the tension in the rope here is the same as the tension in the rope there. All right, so we set up our little free body diagram. The forces acting on M1, well, you have M1's weight, and the only reason M1 doesn't fall and accelerate towards the ground at a rate of g is because there's tension pulling back. Now, the reason I've chosen these signs, the negative with the tension and the positive with the weight, is because the system is moving counterclockwise. Now, if we look at M2, that's a different story. M2 is being lifted by the tension in the string, and the only reason it's not moving up at a rate of A is because it also has weight. So tension is pulling the weight of M2 and accelerating it. So these are your two equations and your two unknowns, and frankly, I'm going to let you do the algebra. You need to solve for A. Maybe the problem asks you to find T. Fine. You know, I'll do it for you. Classic. Add up the left side, and you've got this going on. The T's go away. How convenient. And when you add up the right side, you'll get a sum of the masses times the acceleration. I'm going to be lazy here and skip a step. There is your acceleration for the Atwood machine. Now, if you didn't know what the masses were, like I didn't give you values here. If I didn't know what the masses were and I set up the equation, and then later Kyle said, M2 is 10 kilos and M1 is 5 kilos. Well, then the system would have moved this way. But when you plug in 5 and you subtract 10 from it, you'll get a negative acceleration. Okay, so that just means the fact that it's negative, it's going the other way. Not a problem. Not a problem, peeps. You assumed it went this way. You found that your acceleration was negative. The value of the acceleration doesn't change, just the direction it goes changes. So everything's covered, no problem.